Okay, hi everybody. This is the first video lecture for Sport Science Sports Studies group. We're going to talk about a new topic, which is vectors. I'm working from the PDF notes that are up on the Moodle page, and we'll read through them. Okay. Now it says here, a vector is a column of numbers. Okay, so we'll go with that definition. There are other definitions, which we'll see in a moment. So a vector is a column of numbers. Okay. There's examples here. Okay, so we have one example here, which is a column 3 and minus 4. We have another column, this time a column of length 3, which is 1, minus 1, and 2. And we have another column here, which is a bit more complicated. It's the cosine of some variable t and the sine of some variable t, like that. Okay, so those are three examples of vectors. Okay, so we would say that these first and last ones here, because they have two numbers in them, they would be two-dimensional vectors. So they're two-dimensional. Okay, while the middle one is a three-dimensional. Okay, and the thing about a vector is that there really isn't a limit to how large the number of dimensions can be. The maths works just fine if I have 3 dimensions, 4 dimensions, 50 dimensions. It doesn't really matter. I can make the numbers as large as I want them to be. Intuitively, it's difficult to visualize something in more than 3 dimensions. And I'm certainly not somebody who can imagine multi-dimensional objects in his mind, but we're going to see that it doesn't really matter how many terms there are, how many numbers there are in the vector. We're going to handle them the same way, basically, no matter what. Okay? So it says here, a vector is used to represent any quantity which has a direction relative to some point. Okay? So a vector can be used to represent anything with a direction and a magnitude. Okay, direction would be where something is pointing, where it's going. Magnitude would be relative size. And we'll give an example of that on a picture here in just a moment. Okay, so for example, let's say I take an x and y axis. Okay, draw some vectors in here. Okay, I'm going to draw a vector. And we can see that this blue vector here, and I don't know if the colors will come out clear on the video or not. This is a blue line. The origin is, the axes are black. This blue line here with the arrow on it is pointing in a particular direction. So if up were north and this were east, this is pointing northeast, and it has a certain length. Okay. If I take a red one here, we can see that the red one pointing over here, okay, is going in a different direction, okay, and it has a different length. So these are different vectors, okay, and for two vectors to be equal, they must have the same direction and the same length, okay. So when I'm interested in a vector, I'm interested not only in the direction of the vector, but the length of the vector too, okay. So let's move on here. Sorry, the paper is tearing on me here. Okay. So another thing that we would want to take into account here is that vectors have two operations basically that can be associated to them. Okay. Two basic operations. Okay. The first is that vectors can be added. They can be added together if they have the same dimension. So if they have the same dimension, okay, and I'll show you what that looks like in a picture in a moment. And the other thing is vectors can be scaled. Okay, and we'll talk about what those mean in just a moment. Okay, so they can be added together if they have the same dimension, and vectors can also be scaled. Okay, so let's talk about addition first. Okay, so now vector addition is pretty straightforward. Okay, so here's the idea, all right? Suppose I have a vector which is A with B, and I want to add that to C with D. Okay, so I have A with B and C with D. Okay, now A here is called the first component of the first vector, B is the second component of the first vector, C is the first component of the second vector, D is the second component of the second vector. And the way this works is very simple. We just add the components together. So if A is the first component of the first vector and C is the first component of the second vector, then the first component of their sum is the sum of the first components. We have B and we have D. They're our second components, so we add those together, and we have B plus D, and that's the sum of the second components. Okay, so this is the general rule. I've used A, B, C, and D, but of course I could use numbers. Okay, let's say I take 3 and 7, and I add on, I don't know, -2 and 4. Okay, well then what would I have? I would have 3 plus -2 and 7 plus 4. Okay. okay, which is equal to what? Well, 3 plus minus 2, plus minus is the same as subtraction, so 3 minus 2 is 1, and 7 plus 4 is 11. So 111 is my answer, okay? Very simple, very straightforward, okay? I'll do another one here. I'll do one with 3 components, because why not? We'll go 1, 1, 2, plus 0, 1, minus 3. Okay, what do I have? I would have 1 plus 0, which is 1. I would have 1 plus 1, which is 2. And then I would have 2 minus 3, which is minus 1. Okay, so that's an example with 3 dimensions. We just add component-wise exactly the same way that we've done. Okay, now, okay, I'll talk about how to kind of visually represent these in just a moment, but I want to talk about the basic operations first. And the next one is what's called scalar multiplication. Okay, and scalar multiplication is like stretching or contracting a certain vector based on some scaling number. So here's the example, the kind of rule that works for everything. Let's say I have some number which I'll call k, and I multiply that by the vector ab. So k here is a number, it's a normal number, and a and b are the components of a vector. Well, all I do is I multiply in the components, both components. So I have k times a, and I have k times b. Okay, let me give you an example of that. Okay, so let's say I had the vector minus 2, 3. Okay, minus 2, 3. Minus 2 is the first component, 3 is the second component. And let's say I'm going to multiply this by 4. What would I have? I would have 4 times minus 2, and I would have 4 times 3. Those would be my components. Okay, and now I multiply in both positions. 4 times minus 2 gives me minus 8. And 4 times 3 would be 12. So minus 8, 12 is my answer. Okay? And we're going to talk about vectors as existing with directions. Okay? But really, to a mathematician, a vector is just anything that has addition and scalar multiplication. And there's a lot of things that are not obvious that have addition and scalar multiplication. So vector is a very general term. Okay, let me do another example here before I move on with 3 dimensions. Okay, so let's say I have 3 times the vector 1, minus 1, and 2. Okay, well, what would I have then? I would have 3 times 1, which is 3. I would have 3 times minus 1, which is minus 3. And 3 times 2 would give me 6. Okay? So that's addition and scalar multiplication. So this is graphical representation. Might not be able to put the entire word representation here. Okay, graphical representation. Okay, so we represent a 2D vector two-dimensional vector. In the plane. Okay, and it's very, very simple. Okay, if I have a vector here, which is x with y, okay, x with y, well then its position goes in the plane here. I have x and y axes here, and the x position tells me it's left and right position, the y number tells me it's up and down position, okay, and then I draw an arrow to that point, okay. So this is my plane. Let's do an example of a graphical representation. Okay. So let's do an example here. I'm going to choose xy to be 3 minus 2. Okay. Could I have picked something different? Of course I could have. Okay, but this is the one I picked. Okay, so we need a scale. This is my x-axis, this is my y-axis. This is 1, 2, 3. This is -1, -2. I'm going to draw this vector in red. Its x position, which is its left-right position, is 3. So I'm going to be going from here. Okay, it's going to be somewhere on there, and its y position is -2, so it's going to be along here. And we can see where they cross each other, which is right here at this blue point. Okay, like that. I hope that comes out clear. And then I just draw out to that blue point, put an arrow on it, and that's my vector. Okay. Now, I'll give you another example in just a moment here. So we'll do an example here. Okay, example. Okay, well, let's pick, let's choose xy to be different. Let's choose -1, 2. Okay, so I have my plane here. Okay, this is my x, this is my y. My left-right position is 1 unit to the left. My up and down position is 2 units positive, so about 1, 2, okay, which would put the, I'll draw my lines again just to kind of show you the kind of crossing point. Okay. And I'll draw this one in blue again. I have a point here. I'm going to connect that to the center and draw a little arrow on it. And that's my vector there. Okay. So, what about three-dimensional vectors? Well, I could do the same with three-dimensional vectors, where instead of having x and y, I might have x and y and z. But three-dimensional pictures are kind of hard to draw. Okay, so I'm going to kind of, I'd say I'll hold off on drawing a few of those until I have some nicer pictures prepared, which might take me a little bit of time. Okay, but those are some examples of basic vectors, and we can see that these vectors have a particular length, and they have a direction associated to them as well. And the lengths are not the same. Obviously, this vector is not the same length as this one, and they're pointing in completely different directions. Okay. So how do we how do we work with vectors? Okay, so as we said, there is addition and there is scalar multiplication. Okay, and a scalar multiple is just multiplying by some number, some normal number. Okay, so now how would I visualize these? Okay. Visualizing scalar multiplication. Okay, well, this is pretty simple. Okay. Let's say I have my plane here. This could be in 3 dimensions, but I'm going to work in 2 dimensions just because it's easier and I can draw it more naturally. Let's say I had this blue vector here, which I'm going to just send up kind of northeast. Okay. Okay, like that. That's my vector. And say I want to scale it. Okay, say I wanted to scale it. Okay. So let's say that my green vector is going to be the blue vector multiplied by 2. Okay. Well, what would that be? Well, if I wanted to scale it, all I would do is maintain the same direction and scale the length. Okay. So if I go out the blue vector, I just do that twice, which means I go out to blue and then the same distance again. So I go out here from the origin to this point, and then I move the same distance again. So the green vector is in the same direction, but it's twice as long. Okay, it's twice as long. Okay. And while I've decided to multiply by something bigger than 1, if I wanted to multiply by, say, half, for example, then instead of multiplying blue by 2 to get the green one, I would have taken blue and I would have just shrunk it. Okay, so instead of going all the way to blue, I would have gone halfway along the blue arrow, and that would be multiplying by 1/2. Okay, well, what about multiplying by -1? Okay, and once you understand positive multiples and once you understand negative multiples, you're basically okay. Well, this is really not all that hard either. Okay, all I do is I continue the same vector in exactly the opposite direction with the same length. Okay, so multiplying by a number stretches or shrinks the vector, but multiplying by a negative changes the direction to the exact opposite. So if I'm headed northeast, I'm going to go southwest. Okay, if I were going northwest, I'd end up going southeast. Okay, so that's scalar multiplication. It's not too difficult to imagine. You maintain the same direction. You just either stretch or shrink the length to the required scale for a positive multiple, and for a negative multiple, you reverse the direction to the exact opposite. Okay, now, what about addition? Okay. This is a bit different, but it's not too hard. Okay. So let's say I have my x and y plane here, and I have 2 vectors. I will have a blue vector, which goes to here, and I will have a green vector, which goes to here. Okay. Well, this really is not so difficult to do. Okay. What I do is I travel in the direction described by one of the vectors. I can go blue first, let's say, so I go from 0 to the tip of the blue arrow. And then what I do is I take the green arrow and I move parallel to that green arrow along a particular, an equal distance, okay? So here I would be going something like that if I went blue and then green, okay? And if I went green and then blue, it would look something like that, okay? Okay, and this point here where I end up, right here, that's the same point whether I do blue first and then green, or green first and then blue, okay? And this is called the parallelogram rule because this line is always parallel to this one is always parallel to this one, and together this shape is called a parallelogram, which you might remember from geometry in school. So this is the parallelogram rule. Okay, parallelogram rule. Okay, so blue and green added together gives me red. Blue plus green gives me red. Okay. Blue plus green is red. Okay. So that's how I add vectors together. What about subtraction? Well, subtraction, just remember, means addition of a negative. Okay, so if I was to add on, say, blue and then take away green, I would do blue first and then I would move in the opposite direction from the green vector, the same amount. So I would move along the same line and come back the same distance away. So instead of going out in the direction of green, I would move in the exact opposite direction. Okay. So that's how you can visualize addition, okay, with parallelograms. Parallelogram rule. Okay. Now, that's the basic operations of addition and addition and scalar multiplication. I'm going to stop there, okay, because if the videos run on too long, they fail. And then we'll continue in the next video.